Okay, this is AQA AS Redox Lesson 1. So today's lesson is about oxidation reduction. If you have your official textbook at hand, you can look at pages 156 to 157 to help you with this. So today's lesson objectives, there are 4 of them. Firstly, you need to be able to define oxidation and reduction in terms of oxygen and hydrogen transfer. Then you need to be able to define oxidation and reduction in terms of electron transfer. You need to be able to write half equations, and you also need to be able to identify reducing and oxidizing agents. So we'll take these lesson objectives one at a time. So the first one is to define oxidation and reduction in terms of oxygen and hydrogen transfer. And this is very straightforward. It's an old-fashioned definition, which we don't tend to use anymore, but can still be useful. So when the terms oxidation and reduction were first introduced, oxidation was taken as meaning that it gained oxygen. So either it gained oxygen or it lost hydrogen. Reduction then is the opposite. So it's a loss of oxygen or the gain of hydrogen. Now we can look at some equations to demonstrate this. So for oxidation, if we take 2 coppers, which is Cu, and add oxygen to that, it gives us copper oxide. So the copper has gained oxygen, because on the left hand side the copper is just by itself, and on the right hand side it's chemically joined with the oxygen. So the copper has gained oxygen, so therefore it's been oxidized. So we can then have an example of reduction. So if we take our product copper oxide, we can then undo that oxidation if we react it with hydrogen. So if you take the copper oxide and react it with hydrogen, you end up with copper metal back again, and you also end up with water. So in this case, in the copper oxide, the copper has been reduced, because on the left hand side it has oxygen in, and on the right hand side the oxygen's been removed, and it's back to just being the metal by itself again. Okay, so next lesson objective, we're going to take 2 this time. So we want to be able to define oxidation and reduction in terms of electron transfer, and we also need to be able to write half equations, and these 2 go together. So I'm going to explain them at the same time. So our previous definition was just talking about oxygen or hydrogen. Now we need to talk about electron transfer, which is the one that's more widely used nowadays. Back in your GCSE you'll have heard the expression oil rig, and hopefully you can remember that this means oxidation is loss, reduction is gain. And when we use this expression, we mean we're talking about electrons. So oxidation is loss of electrons, reduction is gain of electrons. So if we look back at this original equation that we looked at, where we had copper reacting with the oxygen, we can look at it in a different light. Because as well as looking at it from the oxygen angle, we can now look at it in terms of the electrons. So oxidation, we said that copper had been oxidized because it joined with the oxygen. But it's also been oxidized because it's lost electrons. If you look at the copper on the left hand side, the copper metal is just a copper atom. Okay, so it's got the same number of protons as it has electrons, so it's neutral. If you look at it on the right hand side, it's become a copper 2+ ion. So each copper has lost 2 electrons. So it's gone from being copper to copper 2+. So it's lost electrons. So from the electron transfer model of oxidation and reduction, it's been oxidized because it's lost electrons. If you look at the oxygen in this equation, you can see that it's been reduced, because it starts off on the left hand side as O2, so it's just an element. Again, it's got the same number of protons as electrons. On the right hand side, it's got more electrons than it's got protons, because it's gained, each oxygen has then gained 2 electrons. Now we can show this by doing the half equations. Now a half equation, as you can imagine, is half an equation. So you have one for the oxidation and one for the reduction. So we can break this equation down into 2 half equations, which I'm just going to show you. So the first one we can look at is we can look at the oxygen. So the oxygen on the left hand side starts off as O2. Now we need to add 4 electrons to that oxygen to give the situation we've got on the right hand side. So you've then got 2 O2- ions. So it's gained 4 electrons. Each oxygen's gained 2 electrons to become 2 minus, and there's 2 of them, so it's gained 4 electrons in total. So in that case, it's gained electrons. So that's the reduction half equation. Now we need to look at the oxidation half equation. Now if we look at copper, so copper starts on the left hand side as Cu, and it ends up as Cu2 plus on the right hand side. So it's lost 2 electrons. So the electrons in this equation have to go on the right hand side because they've been lost from the copper. So this shows that the copper has been oxidized because it's gone from Cu to Cu2+. So it's lost 2 electrons, so it's been oxidized. So those are the two half equations. Now if you wanted to recombine them, you have to have the same number of electrons on the left-hand side as the right-hand side. So on the bottom one for the copper, you can see there's only 2 electrons, whereas on the top one there's 4 electrons. So you have to multiply the bottom equation by 2, which would give you 2Cu to 2Cu2 plus 4 electron minus. And then you can then recombine them, which is just adding them together to give the original equation. So now we can do this with the second equation that we looked at as further practice. So again, just to remind you, we had copper oxide reacting with hydrogen, and that gave copper, and it also gave water. So when we looked at this in terms of oxygen gain or hydrogen loss, we said that the copper oxide had lost oxygen. So because the copper oxide had lost oxygen, it had therefore been reduced. But now we can look at this in terms of electrons. So on the left-hand side, the copper starts as Cu2+, and on the right-hand side, it's become copper metals by itself. So the copper 2+, so the copper goes from 2+ to just a copper atom, so it has gained electrons. So because it's gained electron, it's been reduced. So the copper's been reduced in this case. So we can do the two half equations. So the copper 2 goes from copper 2+ to copper on the right hand side, and that gives us our half equation. That's giving us the reduction half equation because the copper 2+ is gaining electrons, so the electrons on the left hand side, so it's copper 2+ plus 2 electron minuses goes to copper. The other half equation is H2 on the left hand side going to 2H plus on the right hand side, and that should be a plus 2 electrons on the right hand side. Sorry about that. So in that case, the hydrogen's gone from H2 to H plus, so it has lost electrons, so the hydrogen is what's been oxidized. So the copper 2+ has been reduced, the hydrogen has been oxidized. Now in this case, you'll see that in the overall equation there's oxygen. In these two half equations there is no oxygen, and the reason for that is that O2 minus is what we call a spectator ion. So if you're a spectator at a sport, you are just watching it, you're not taking part. So a spectator ion is an ion in a redox equation which isn't taking part. So the O2 minus, if you look on the left hand side, it starts as O2 minus. If you look on the right hand side, it's still O2 minus. So it hasn't changed in terms of electrons. It's exactly the same on the left hand side as it is on the right hand side. Yes, it's chemically combined with a different atom because on the left it's combined with the copper and on the right it's combined with the hydrogen. But in terms of electrons, it's exactly the same on the left hand side as the right hand side. It's O2 minus on the left and it's O2 minus on the right. So it's a spectator, it hasn't got involved. So therefore it's not in either of the two half equations. Okay, so the last thing you need to be able to do is to identify the reducing and oxidizing agents. So if we look back at this original equation we had 2 Cu plus O2 giving 2 CuO. So the copper is reacting with the oxygen to give copper oxide. So we said that the copper was being oxidized. Firstly, because it's gained oxygen, but also because it's lost electrons. So because the copper has lost electrons, the copper is losing those electrons, it's giving those electrons to oxygen. So oxygen is gaining electrons because it got them from the copper. So the copper is then a reducing agent because it is making another chemical gain electrons. So copper is the reducing agent in this equation. As you might imagine, oxygen is the oxidizing agent, because oxidation is loss of electrons. So oxygen, because it's gaining electrons, is taking those electrons from the copper. So oxygen is removing the electrons from the copper, so therefore it's acting as an oxidizing agent. And it's important not to get mixed up between what's been oxidized and what's been reduced, and what's an oxidizing agent and a reducing agent. So the general rule is, if something is being oxidized itself, it will then be acting as a reducing agent. If something in an equation is being reduced itself, then it will be acting as an oxidizing agent. So we can look at this equation being split up into two. So again we can write the half, this was what the half equation was. So the oxygen is taking the electrons and becoming O2 minus. And the copper is then going from copper to copper 2 plus. Okay, so this is the second equation that we had. So copper is going from copper 2 plus to copper, so it is gaining electrons. So the copper on the left hand side in the copper oxide has gained electrons, so therefore it's been the oxidizing agent. Whereas the hydrogen is going from H2 to H plus, so it's lost electrons, so therefore it's being the reducing agent. So again we can look at the half equations to show that that's happening. Okay, and again O2 minus is a spectator ion, as we said before. Okay, so these are our lesson objectives, and we should now be able to do each of them. So we said we should be able to define oxidation and reduction in terms of oxygen and hydrogen transfer, so you should be able to do that now. You should also be able to define oxidation and reduction in terms of electron transfer. You should be able to write the half equations now, and you should also be able to identify the reducing and oxidizing agents.